In this lesson, we're going to talk about some differential equations. So the thing that you want to associate here is, in terms of mathematics, when we say the word differential, we can also think in terms of derivatives. So just kind of keep that in mind. So when we talk about a differential equation, we're going to be talking about an equation that involves one or more derivatives. And the solution is actually a function that fits the criteria in the equation. So what's meant there? Let's take a look at this example problem. So here I have a differential equation because if you'll notice, I do have derivatives involved. So that makes this a differential equation. Okay, now because of that, we need to think about a couple of things that might be a little bit overlooked at different points in mathematics and make sure we fully understand. So there are two variables here. We have x, and this is known as an independent variable. So that's our independent variable. And what that means is we get to choose the value of the independent variable, and the y variable is dependent upon that choice. So we call that y variable the dependent variable. Now, a lot of times we use a function notation, so just a general rule of thumb for graphing, that the y variable is defined as some function of the x variable. So y is equal to f of x. Now, in mathematics, really variables can also be functions. It's just a matter of how you need to interpret things at a specific point in time. This is sort of the key thing for substitution. All right, so we can also think of y equals f of x as just a function of its own. We can just think of y as itself a function of x with its own derivatives and what have you. So we don't necessarily have to have a value f of x written in, like this would be some function second derivative, and this would be the function itself. We don't have to have an explicit function written, we just have to understand that y is a function already. That's how we're thinking in terms. Now, there's ways of developing a solution to a differential equation, but I don't want to get to those just yet. I will in a moment. The first thing I want you to do is just really understand what it means to be a solution. So for instance, I'm just going to tell you what the solution to this differential equation is. So the solution here is y equals 3e to the 2x plus e to the negative 2x and minus 3x. And don't worry about how I came up with that. There are methods that could determine that for us, but we're not going to get into those. I just want you to see how the differential equation works itself. Now, y is, of course, a function of x because here I have the variable y equal to some function entirely of x. So I can think of this function as f if I wanted to call it that, or I can just leave it named y. It doesn't really matter. Now, what I want you to be able to do here is understand what it means to be a solution. So let's just show that this is a solution. So show this is a solution. Well, to show that this is a solution, what we would do is we would substitute. The substitutions we would make depend on the criteria in the equation. So we need to take the second derivative of the function y minus 4 times the function y minus 12x equals 0. So we need the second derivative of y. Well, let's get started. So the first derivative of y, you can't get a second derivative without a first. The first derivative, we just go through term by term. So 3e to the 2x. So this is going to be the constant multiplier 3 times the derivative of e to the 2x. And e to the 2x would be itself times the derivative of the inside part, and the inside part, of course, is the exponent, and the derivative of 2x is 2. All right, similarly, the derivative of e to the negative 2x would be negative 2 times e to the negative 2x. It's just itself times the derivative of the inside part. And the derivative of negative 3x would just be the constant multiplier negative 3. And simplifying that, because we are going to take a second derivative, let's make it as simple as we can. That would be 6e to the 2x minus 2e to the negative 2x minus 3. And the second derivative then would be, you can follow what I did, but ultimately it will end up being 12e to the 2x plus 4e to the negative 2x, and the derivative of the constant, negative 3, would go to 0. Okay, so let's go off to the other side here and start plugging things in. So I have y prime as this part right here. Sorry, y double prime as this part right here. I'm going to plug that in for y double prime in the original equation. So it will look like 12e to the 2x plus 4e to the negative 2x. So that's y double prime. Then it's minus 4 times y itself. And y was, of course, 3e to the 2x plus e to the negative 2x minus 3x. And then minus 12x. I'm running out of space here, but I'll just make that equal to 0 as best I can. Okay, so then we've plugged into the differential equation, so we have this statement right over here. We've just simply substituted in for the second derivative of y and y itself. Let's see if this statement works out. Let's see if all of this really does equal 0. Well, we'll expand first. So let's see, 12e to the 2x plus 4e to the negative 2x. You might be tempted to try and combine those, but with the exponents being as they are, there's not really much you can do here. You'd have to work with some fractions. You probably could do something, but it's not going to be as simple as you might think. Most people would make a mistake here would probably try and say that e to the 2x and e to the negative 2x add up to 0, which they don't. So we can, however, distribute this 4. So minus 12 e to the 2x, and then minus 4 e to the negative 2x, and plus 12x. And then we have this minus 12x here and equals 0. And now, if you look, we've got a lot of things that cancel. 12x and negative 12x certainly cancel. Positive 4e to the negative 2x, negative 4e to the negative 2x, and these two terms. Those all cancel out to 0, so that means the entire left-hand side of this equation is 0, and the right-hand side is 0, so therefore, this checks out, and this is, in fact, right here, a solution to the original differential equation. Now, again, I did say that I wasn't going to show you means of determining how to come up with solutions of differential equations. That in of itself is not just one course, but many courses. We are going to develop a technique that will be very helpful to us, and that technique is called the separation of variables. So the separation of variables is a technique used to solve simple differential equations by rewriting it so that each variable occurs only on one side of the equation, and then we use integration. All right, because if a differential equation involves derivatives, the way we're going to get the function y by itself is taking integrals. So it will always involve integration. Now, one thing to keep in mind is that y prime can also be written in the form dy dx. All right, so we have the Newtonian form and we have the Leibniz form. The Leibniz is generally more instructive in most cases, although the Newtonian, I think this is technically Newtonian. I'm not really sure. I've read different pieces. Doesn't really matter. That's what I'm going to call it. It is more compact to write, but it's not necessarily as instructive. So here's what we're going to do. For separation of variables, if it's written in the y prime form, we do want to switch and rewrite the equation in the Leibniz notation. So dy dx equals square root of x over 3y. Because the thing is, we are separating our variables. So we have an x within this dx, and we have a y within this dy. We've got to separate those things. And the way we're going to get away with that is really not that difficult to do. We'll just treat it as if it was its own entity. Even though these are infinitesimally small quantities, we're going to treat them as if they're just normal numbers. So if I take the 3y in the denominator, multiply both sides by that, and multiply both sides by the dx in the denominator over here, and watch what will happen. So when I multiply both sides of the equation by 3y, I will cancel out the 3y on the right-hand side, and that will leave me with 3y dy on the left. When I multiply both sides by dx, it will cancel it out in the denominator. I didn't mean to do that. Oh, I knew that would happen. Sorry. It will cancel out the denominator here, and then leave me a factor of dx on the other side of the equation. So here's what I end up with. Now, a couple of things. So first off, if you'll notice, everything involving y is on the left-hand side of the equation, and everything involving x is on the right-hand side. So we've now separated our variables. That's what's meant by the terminology here. I could have left the 3 in the denominator over here. It doesn't really make any difference because it's a constant. However, it's going to have some advantage in bringing it over here because pretty much it's not a fraction. That's really all there is to it. There would be some additional advantage in rewriting this as x to the 1/2 power instead of writing it as x to the, or the square root of x, because eventually we're going to do some integration work and it's going to be easier to have that written in terms of the power rule. But ultimately, once you have your variables separated, then it's time to do some integration. Now, you don't see any integration symbols, but you do have this hint of these dx's. And these are derivatives. And whenever you have derivatives in your equation, you're going to get rid of them by doing integrals. And this probably looks kind of funny. How in the world do we get away with just simply integrating both sides of an equation? Well, integration is technically a form of a function. And you can do any function you want to both sides of the equation as long as you do it to both sides. And that's perfectly fine. It won't affect the final answers. It made sense way back in early algebra. Of course, we can add 3 to both sides if we wanted to, or multiply by -12 to both sides of an equation if we want to, but once we get into more advanced stuff like integration, it might not make intuitive sense right off, but if you think of it as a function, you can do any function to both sides of an equation, and that's okay. So that's what we're going to do. We're going to integrate both sides. So when I integrate, what's going to happen, the 3 in this case is just going to come off to the side, and then I'm effectively integrating y with respect to y. So that's going to be y squared divided by y, and it's technically plus some arbitrary constant. I'll tell you what to do with those in a second. Then next we have x to the 1/2 dx. That we would integrate using the power rule again. So x to the 1/2 plus 1 would be x to the 3/2 divided by 3/2 and plus some other arbitrary constant. Okay, now we want to get this equation as simple as we can, and I already have just made a mistake, and I'm so sorry for that. I'm sure you noticed it and probably were questioning. Why did I put y in this denominator? I don't know. It was supposed to be the exponent 2. All right, so that's fixed. Moving on. So we will then start simplifying. So I can just write this side as 3/2 y squared. And I'm going to move this constant to the other side, just because, really, that's my answer. All right, now, dividing by 3/2 would be a lot nicer if I was instead multiplying by 2/3. And then I have c2 minus c1. Well, there's something interesting about these arbitrary constants, and this will happen many times over in differential equations, and it'll probably make you pull your hair out at some point. But the arbitrary constant c2 minus c1 is just as arbitrary as any old constant. So really, you can take the conglomeration of these arbitrary constants and just combine them into a single arbitrary constant. It looks like it shouldn't be mathematically possible, but it absolutely is. It's just an arbitrary constant. You can group it together. It's fine. You don't have to keep track of those things. In addition, you could do something like, for instance, if I multiply both sides of this equation by 6, then what would happen, come up over here, is I would end up with 6 times 3/2. I'm just basically choosing 6 to get rid of the denominator. So 6 divided by 2 is 3. 3 times 3 is 9. So I could write this as 9y squared equals, then 6 times 3 is going to be 2. 2 times 2 is 4, so this would be 4x to the 3/2. And then you might say this would be 6 times c. And you're not wrong, it's just 6 times c is just as arbitrary as c itself. So it's going to look a bit strange, but we'll just write c. This is a perfectly valid answer to our differential equation. I'm going to write it in a slightly different form. I'm going to get all variables to one side. It's not really a necessary move for simplification. I'm just simply going to write it this way, just because. And you might be thinking, where do I stop the equation? Well, to be honest, once you have a valid form of the differential, you're done. You're really finished. You could have finished back here at this step. It's just this one involved fractions, and I saw a way that I could get rid of those fractions, and I think that this one looks nicer. So once you have the differential, you're free to stop wherever, but it might make it easier to work with later on if you take a few additional steps in simplification. As long as you have an algebraically equivalent answer to what's provided online or in the back of the book, whatever mode you're taking the class, that's perfectly fine. Now, another topic we need to revisit when it comes to solving differential equations is the concept of general and particular solutions. All right, so a general solution to a differential equation involves the arbitrary constant c in the solution. So what I found just a second ago was the general solution to that particular differential equation. And I could state it as such. So my general solution to the prior example was 9y squared minus 4x to the 3/2 equals c. What this represents is a family of curves. And so the family of curves that fits the criteria all basically look like the same function, but could be off by an arbitrary constant. What we want to do is we want to find one particular solution that passes through a specific point. So here's a quick visualization that might help you understand exactly what's happening here. So what I have is a function that I've graphed the family of curves. So I have a base function, x cubed minus 2x minus 1. Now, clearly that's not the same one that's been used in this example, but to graph 9y squared, plus 4x to the 3 halves will be a bit more advanced. So I've got a simpler function to work with. So just assume that I'm basically graphing this function as a solution to a differential as a general solution. So I have a plus c. So that value c can be anything. And whatever c is, and I've got this coming from just different integer values, but it could be fractional or decimal or what have you. But whatever that value c is, the curve would have the same basic shape. You can see that all of these have the same basic shape. It's just shifted up or down. That's the only thing that constant would do. Now, for all of these curves, there would only be one value that actually passes through a specified point. So let's say I'm interested in the one particular curve that's passing through the point 1, 7, and I'm just making up a curve value, for instance. So I'm looking for the one curve that would pass through the point 1, 7. So 1, 7 would be, like, here's 1 on the x, 7 on the y would be about right here. I think it's this one that I'm choosing. Let's see what happens. So if I solve this, then actually it's a little bit higher. So what this is saying is the curve that would actually pass through, whoops, you know what, I think, there we go. So the curve that actually would pass through this particular point would be this curve. And that's the only one out of all the possibilities that would pass through that point. So that's why we call the curve with the plus c the general solution, and the curve that solves a specific initial value a particular solution, because it's just one particular curve that would pass through that point. So to actually solve for that particular curve that passes through a particular one specific point, here's what we need to do. We need to have an initial value, and the initial value is going to contain an x and a y. Now, sometimes you're given a function and an x value, which you can compute the y value from that. Sometimes it might say, like, find the curve that passes through the y-intercept, which you would know, for instance, it should tell you what the y-intercept value is, but that the x would have to be 0, something of that nature. But you need an x and a y so that you can plug those values into your general solution. So when we plug these into the general solution, we would get 9 times the value 1/3 squared, because y is 1/3, minus 4 times 1 to the 3 halves power equals the constant c. So this is effectively 9 times 1/9 minus 1 times anything is just 1, so just minus 4 equals c. So 9 times a ninth is just 1. 1 minus 4 is going to be -3. So what we found is the one particular curve of this general solution that happens to pass through the point 1, 3. So that particular solution, whoops, misspelled that. That particular solution is 9y squared minus 4x to the 3 halves equals -3. And of all the curves that represent the general solution for this differential, this is the only one that passes through the point 1 and 1/3.